Before a single drop of water overtakes the spillway of a modern dam, the structure's survival depends on calculations made long before the storm formed. Modern hydrological design has moved past pure empiricism. Engineers no longer build massive walls and simply hope they hold against the elements. Instead, the discipline demands the precise collection of field data and a rigorous understanding of the underlying science. That science begins on the ground with the rain gauge network. To capture accurate precipitation totals across a massive catchment area, hydrologists must deploy a dense physical web of measurement stations. This diagram shows the Simons rain gauge, a standard piece of non-recording field equipment. It captures the exact vertical depth of precipitation utilizing a precisely dimensioned funnel and metal casing set atop a heavy concrete slab. If the density of these stations across a basin is inadequate, or if the physical measurements are flawed, every downstream calculation is compromised. Predictive models simply cannot function without a highly accurate baseline. Gathering historical rainfall totals is only the first step. Before an engineer can trust this information to size a dam, the raw numbers must undergo rigorous statistical processing. A list of daily precipitation depths cannot protect a concrete spillway. That raw data must be mathematically transformed into actionable engineering intelligence. The very first check performed on raw rainfall data is for continuity and consistency. This page of notes illustrates the double mass curve, the graphical method used to verify that consistency. By comparing stations against a standard, engineers verify that the data comes from the same parent population over time, isolating inconsistencies caused by shifting instruments or observational errors. Yet, perfectly consistent historical records are not enough. Engineers cannot size critical infrastructure based merely on average annual rainfall or typical seasonal storms. Infrastructure faces its true test during what hydrologists term an unusual meteorological combination. These are catastrophic events, like a cold air mass conflict occurring simultaneously with extreme thermal convection, that statistically shouldn't happen at the same time, but occasionally do. Because these extreme outliers rarely exist in historical logs, data alone cannot guarantee the structure's survival. The engineer must apply matured judgment to model the absolute worst-case scenario before pouring any concrete. This presents the central challenge of hydrology. How do you translate a chaotic, unpredictable storm into a discrete, highly predictable mathematical curve of water runoff? The solution is the unit hydrograph theory, the foundational mathematical model for calculating direct storm runoff across a given basin. This slide defines the unit hydrograph. It represents the exact direct runoff resulting from precisely 1 centimeter of effective rainfall applied at a uniform rate over the entire duration of a storm. For the math to work, the theory relies on constraints established by Leroy Sherman. First, the effective rainfall must be uniformly distributed over the entire catchment area. Second, the rainfall intensity remains constant over the specific time duration. Third is time invariance. The physical shape of the catchment's response depends entirely on the terrain, independent of what season the rain actually falls. Finally, the most critical constraint is the linear response. Because the basin's variables are held constant, the principle of superposition applies. Here is how that linearity works in practice. If a 1 centimeter storm produces a specific base hydrograph curve, a 3 centimeter storm can be calculated simply by scaling the ordinates of that baseline curve upward by a factor of 3. By standardizing the physical terrain into a constant, the unit hydrograph converts discrete, scattered raindrops into a continuous mathematical threat that can be infinitely scaled. Real-world storms rarely cooperate with Sherman's constraints. They are almost never perfectly uniform in intensity or duration, requiring engineers to move away from discrete logic and adopt continuous mathematical routing. To model these complex catchment responses, hydrologists utilize the Instantaneous Unit Hydrograph, or IUH. One approach is the Clark model. It solves for rainfall non-uniformity by routing an instantaneous inflow of water through specific time area zones, known as isochrones, translating the water into a linear reservoir. This allows the Clark model to simultaneously calculate the physical translation of the water across the basin and the natural attenuation or flattening of the flood peak as it moves forward in time. An alternative is the Nash conceptual model. Instead of time area zones, Nash abstracts the physical catchment completely, dividing it into a cascade of identical reservoirs. The outflow from the first reservoir acts as the immediate inflow to the second. This mathematical routing cascades sequentially until it yields a perfectly continuous output curve at the base. This continuous mathematics represents a violent physical reality. It predicts exactly how floodwaters surge through steep, rocky river valleys, rapidly multiplying in volume and kinetic energy as they approach a choke point. Abstracting a sprawling, chaotic basin into a series of mathematical reservoirs is what allows engineers to precisely predict the peak flood discharge threatening a dam. Once that peak discharge is calculated, the predicted flood load must be strictly categorized in order to safely size the dam's spillway. The first category is the standard project flood. This is an estimate of the most severe combination of meteorological conditions that are reasonably characteristic of the specific drainage basin. Then there is the probable maximum flood. This accounts for the absolute extreme, catastrophic weather event and is a load condition specifically mandated for the spillway design of very high-hazard dams. The standard project flood typically sits around 80% of the probable maximum flood. However, designing any structure for absolute 100% protection against the rarest events is economically impossible. Therefore, the ultimate engineering objective is not zero risk. It is quantifying the exact mathematical probability that a given design flood will be exceeded during the structure's useful life. This displays the binomial probability theorem. P equals 1 minus the quantity 1 minus 1 over t to the power of n. Applied to a 10-year project and a 15-year storm, Step 1 finds non-occurrence risk. Step 2 compounds it. Step 3 calculates final probability, yielding exactly 49.83%. This exposes the harsh reality of the discipline. Civil engineering is never about guaranteeing absolute safety. It is about the rigorous, mathematical management of calculated failure risk. But what happens when an incoming storm exceeds those mathematical probabilities? What happens when the engineered structural limits of a basin are completely maxed out? When physical infrastructure and routing models offer no further protection, hydrologists must turn to active atmospheric intervention. The primary method is cloud seeding, an aggressive technique deployed to force premature precipitation, actively managing the moisture inflow index before the storm ever reaches the critical catchment area. It works through mechanical injection. An aircraft flies beneath a supercooled multi-cell cloud, injecting silver iodine flares straight into the updrafts. Once inside, these particles bond with water vapor, triggering the rapid development of heavy ice crystals. This effectively forces the cloud to yield its payload early. These operations are not theoretical. Teams of pilots and meteorologists have successfully deployed this technique to mitigate extreme hydrological threats across the globe, including large-scale operations over Karnataka, India. The atmospheric seeding forces a thick storm cloud to release a sudden, massive deluge of rain over an entirely different landscape, sparing the infrastructure downstream. The discipline of hydrology has evolved into a two-front defense, mastering the predictive mathematics of the ground and the active manipulation of the sky.